Hello, what's up, guys? Today we are going to continue with our Abaqus tutorial, and today's topic is a plate with the U notches, right? You can see this is the plate. These are the U notches. We have two, this one and the other one of a radius of 15 millimeter, right? So what I'm gonna do is to model first the geometry. So I have this plate. As you can see, it's a 2D model. This is not what I'm going to consider. You can see this isometric view. I'm going to model my simulation for with the 3D model, right? I don't want to use the 2D. I just want to use the 3D one because it's very easy for me. It's not a complex geometry, and also I just prefer today to use this because the previous tutorial I only use 2D model, right? So this one is going to be a 3D. So I already designed my geometry on Katia, so I can just import it. I go here, file, and then I go import, not a sketch, but a part. And I'm going to search for the location where I saved my geometry. So it's here. But the thing is, my file is a step file. So you click here. So now I have my plate. You click, you double click. So you have the ability to change the name here. So you have this option. You can also keep this name. You can go here on OK, and that's it, right? So you have your geometry. So the second thing is the property, okay? Nothing with the part because it's already here. You can come here and the tree and you can have your part here. So second is the material here or the property, okay? So you can click here. You can also come up here and pull property. It's same. You click and then you give a steel. Know that my geometry is on millimeter. So as it's on millimeter, I'm going to give 7.9 power of -1. And you go mechanical, elasticity elastic, the Young modulus 210,000 megapascal, and the Poisson ratio is 0.3. And that's it, okay? So now let's create the section 1, so it's homogeneous. You go continue, and okay. Now we will assign the section. You hit here, you click your model, you hit done, and you have the section. If you want to create another section, you can click here and create another one. But we will use the one that is here, and we hit OK. And you can see the changing color here. That means the section has been assigned successfully. So the third thing, assembly, you will always create an instance in order to have your model. So now we're fine. So then you go on step. So the step is very important because it's where you will tell the steps that you will have on your boundary conditions or loading, right? The initial here, it's a default one. It's already there. You can only use it for boundary condition, but for loading, so I create a step for loading is the one you can use for loading pressure and stuff because only a boundary condition for the initial, but the other things to apply, you use the steps. You create a step. So for loading, right? So it's a static general here. For example, if we wanted to do a dynamic analysis, we'll come here and hit dynamic, hit transfer it here, but it's a linear static analysis. So you hit here, static general, continue. So now you go here, no incrementation 0.05, and the maximum is 1. So I'm okay with this. So let's hit OK. I already have my step, so I can go and apply my boundary condition and loads, right? So you go here, you hit loads, you give a name, which is a pressure, a traction, right? So that's what I apply. This is 100 megapascal that I apply in this phase here. So that's what I'm going to do. So it's a pressure. And the steps, you can even start it with the initial, but you cannot use the initial because it's a loading, right? You use loading here so you can use the pressure. Only boundary condition that you can use the initial. So you hit here, and then you will click continue, you hit the face, you hit done, and then you give the magnitude, which is 100 megapascal. If, for example, now, because this is ramp, you can create an amplitude here and tabular and stuff. But if you guys are interested, you can ask me below. One day I will make a special tutorial for this. But as for now, let's use the ramp. That means the load is constant and applied directly instantly. It's applied instantly. There is no amplitude for it. So, okay. But you can see the direction of my pressure is going in. So it's a compression, but I want to apply a traction. Let's go on the manager. You hit edit and you put a minus here. You put a minus, you hit OK. You can see now the change in direction. So now boundary condition. So it's a fixed support. So let's give fixed support. So you can just keep this, you go continue, you will select the face, this face right here, you hit done, and then you go down here, encastrate, that means it's a fixed support. So you block all the translations and all the rotations. So now we finish with the loads and boundary condition. Let's go on mesh. So this is a simple structure, simple geometry. So I don't really have to put many things. I mean, many parameters about the mesh. They just go and generate it directly by the camera. You go here on part, and you click this one and select the global size. I think 10 is perfectly fine for first runs of a simulation. Let's go for this first and see. So we will compare with the analytical solution. So with the analytical solution, we can see if we need to adjust the mesh or not, because you can see here, we can refine in this area, because in order to have accurate results, you need to refine where you have some I mean, when you have these notches here, you need to refine in order to have those accurate results. But let's go on job directly. You hit job here. So this is the first run, because we will potentially do another one, but depends of the result we have. Continue. So I think the name here, you need to put underscore. Abaqus doesn't accept the space. So you go continue, you hit OK. Now you go back on manager, you hit submit your work. And let's wait for result. So now our simulation is complete. Let's go on result here and hit this. And you can see the values that we have is 164. So 164, and let's go and use this 164 megapascal. That's what I mean. So let's go with the analytical solution and see. I prepare Python code here. So you can see all the infos that we had about the geometry. I put it here, and I use the formulas that we use in order to calculate the maximum stress, So let's hit run the code, and let's see here the results. So yeah, it will come in a second. So we have here the maximum von Mises stresses is 300 megapascal. So this is really far from what we have here, because we have 1 and 64, and the analytical is 300 megapascal. So the reason that the results are not accurate, because the analytical one are the best results for now. Because here in our simulation, the mesh is not refined around these notches. So let's go on the mesh and refine this area, and I bet we'll have better results. So let's go on mesh. So you hit this, you go and select this edge, and then I will turn around a little bit. You hold the shift button here in order to select all these edges at the same time. And you hold the shift button, you hit all these, and you go here and you put, let's say, 3. So we'll have very refined area. Okay. So delete the meshes here, you have this. So let's go on the global one, and we can still go higher here. Let's go 18 or 20, because the Global mesh is not what we are really interested, but what we really want. Let's go. I think 20 is really. Let's go 18, for example, and hit OK. So what we really care is about this area around the notches, okay? But the other side is not what we really want. So let's go and see. So now we have a larger mesh in all the other area that is safe, because here it's not critical. What is critical is here. That's why we need to refine in order to have a better result in this area, because the other ones here we don't care. So I bet we have closer results with the analytical solution. Let's go and run here, job and run. Let's create another one, and let's say second run. Okay, I mean second simulation, continue. Okay, and let's submit our work, and let's wait and see. So let's go for results. See, so you can see we have 255. So this is more close. I mean, it's closer to the analytical one. The analytical one, don't forget, is 300. And 300 and 255 is not far. It's just 5 megapascal less. So it's really better. So I bet if you refine really tiny here, if we make a very fine mesh than this, maybe you will have the 300 megapascal here, or 269, or no 259 or something. But this is fine. I just wanted to show you guys the way you compare analytical results and numerical results. So I think that helps. If you want to create graphs, you can ask me below. I will tell you. This is the option that we use for the graph creation.